Okay, now I want to talk about free body diagrams. I'll sometimes refer to them as FBDs. Sometimes you can see them called force diagrams. And a free body diagram is really just a pictorial description of the forces. And I'm going to actually write force vectors, because we're going to draw these as vectors. Sometimes you want them to scale. Oftentimes, just a rough estimation is all you need. And in order to draw them, you're going to start with either a box or a dot. Sometimes you can put a dot inside a box. There's a few different ways to draw it. But just imagine this. If you look at an object, you want to visualize the forces acting on that object. So let's just think of a book sitting on a table, right? The book sits on a table. It's a flat surface. And we know there are a couple forces that act on it. We know that there is a force of gravity, known as the book's weight, that pulls it down. Gravity always pulls it down. As long as you are on the surface of the Earth, there's going to be a gravitational force. But we know that that book has to be in a balanced situation, right? It's got to be in equilibrium. And how do we know that? Well, the book's staying at rest. It's not accelerating down into the table. If it started burrowing down into the table, that would be a problem. So we know that this downward force has to be equal and opposite to an upward force. And that upward force is the force of the table pushing on the book. Whenever you get a flat surface pushing on an object, that would be considered your normal force right there. So this is what the free body diagram of that object looks like. There's lots of ways to draw free body diagrams, but they help you visualize problems. For example, let's say instead of a book at rest, let's say that book is moving rightwards at a constant speed. Now there's a couple ways this could happen, but in real life, if it's moving rightwards at a constant speed, it's because you're applying a force to it. And the reason that you have to apply a force to it is that there is a frictional force that resists your applied force. So if you want it to stay balanced, meaning you want the net force to be zero, you've got to apply force that's equal and opposite to the frictional force. Let's say instead, though, it's moving on a frictionless surface. Well, if it's frictionless, you no longer have a force of friction. We'll ignore air resistance as well. And it turns out that the free body diagram for this looks exactly the same as the free body diagram for the object that is at rest on the table. And this is just a fancy way of saying that you don't need a force to be pushing on an object for it to be moving in that direction. Remember, acceleration and velocity mean two different things. If this is moving, for some reason, it's already gotten moving, and it's moving at a constant speed, you don't need to push on it anymore if there's nothing to resist it, if there's no friction. Imagine instead, though, an object is moving right and slowing down. Slowing to a stop. So if I push something to the right and it slows down, it's got to slow down because there is a force of some sort, often friction, that is pushing it to the left. So for this, your free body diagram might look like that. You've got a frictional force to the left that's slowing it down. So even though it's moving to the right, there are no rightward forces. Nothing is pushing it to the right anymore. It's just slowing down to a stop, like skidding to a stop. It's on the Earth, so there's going to be a gravitational force, its weight. It's on a flat surface, so you're still going to have a normal force. That is what the free body diagram would look like. You'll notice each of these is helping to describe the forces. If you ever get stuck on a problem, try drawing a free body diagram, and it will help you oftentimes figure out what's going on. Maybe a book is thrown in the air. What is it going to look like? Well, if it's near the surface of the Earth, it's going to have a gravitational force that's towards the center of the Earth, in that case downwards, right? Let's ignore air resistance. So I'll say no air resistance. Then on a flat surface, no. Is it being pushed or pulled by anyone? No, it's already in the air, right? Maybe it had to get pushed or pulled to get in the air, but once it's in the air, nothing else is pushing or pulling on it. Any cords or wires? No, no tension, right? We're ignoring air resistance, so that means we also ignore buoyancy, which we're not going to really deal with in this class anyway. So it turns out that the free body diagram for an object in the air is just this. That's it. Because the only force acting on it is gravity. It's not balanced, right? If you throw it in the air at the top of its arc, gravity doesn't go away. So your force is always, always down. And this is why for the free fall, when we looked at free falling objects, it's this net force. In this case, your net force is equal to your gravitational force. Because there's only one force, so because there's only one, they have to be the same. And this causes your net force. And we know your mass times your acceleration is your net force. And your acceleration, if you're falling, is 9.8 meters per second squared. That means the weight of any object is going to be m times 9.8 meters per second squared. And we'll get into that a little bit when we talk about weight. I think that's it for free body diagrams now. You're going to get more practice on this in the future as well.